Hello and welcome back. So now that we've gone over what it takes to calculate a loss function, we're going to go over the process of optimizing over that loss function to train our model. So we're going to go into a little more detail on gradient descent and just breeze over a comparison of the different optimization algorithms. Most of them are options you can choose from. There are in Keras and TensorFlow. It's really a parameter that you can put into your model. So let's make sure that we understand the intuition behind optimization. Recall that we calculated for a loss function L, where L consists of the data loss and some regularization loss. Now, you can take a graph of the loss function and you can call it the loss landscape. This function is defined over many dimensions. Let's use a pretty common illustration for easier visualization. Think of the loss function as something three-dimensional that we are seeing here through an image, where the blue spot here is the valley or the lowest point of this shape, and this, and this, these are the highest points. So this is almost like a bowl that you're looking at from the top. Trying to minimize the loss, the specific loss of one set of parameters W is like finding the value in the loss landscape. You want your values W to be such that your loss is minimized here. But remember that W can take the weights can take many different values, which is why we have a landscape to work with. So let's think about our static y equals wx linear classifier. Once you calculate the loss for one set of values W, you kind of end up at one point here. So how do you, from here, optimize down to here? You want to take a step in the direction of steepest descent and keep going until convergence. So what does convergence mean? An algorithm converges if the output approaches a certain value no matter how many steps you iterate on. So here, imagine that we're looking at our bowl from the side. It takes a step, takes a step, takes steps, takes a step, but each step, the distance is a little bit smaller, and eventually, no matter how many additional steps you take here, you're not going to move beyond this point. That is convergence. And ideally, we want our algorithms to converge at the global minimum of the loss landscape. We don't calculate the loss landscape when we do deep learning. What we're trying to do is have a good enough estimate, find values W that make sense for us. How do you calculate the direction of steepest descent? So you do that by taking the derivative of the landscape around you. Imagine if you were a person and you were dropped into that valley, blindfolded at some random spot. How could you gradually walk down to the bottom? One way you could do it is stick your foot out, feel the ground around you, see which direction is the steepest direction, and take a step in that direction. The calculation of the local gradient around you, that is a huge idea. That's like a huge principle of optimization. There are many different types of optimization algorithms. The most common ones you'll hear about are batch gradient descent, stochastic gradient descent, mini-batch gradient descent. There's a couple of very interesting, very useful ones that have come out lately. Momentum, Grad, which is the standard right now for TF, and Atom. So I won't go into too much detail on each of these. Effectively, what you need to pay attention to is that the optimization algorithm has a few hyperparameters. It has your parameters theta. These would be your weights, updated weights W. There's a learning rate and step size. So the change in step size was one of those hyperparameters that you have to keep an eye on, that you have to define and tune properly as you build your model. And then you have your cost function here. Learning rate, a little bit of a sidebar. The learning rate hyperparameter is a bit tricky to tune. There's no direct way to measure what the ideal learning rate is. There are some rules of thumb. Every model should have a little bit of documentation on what learning rate seems to work best. One of the ways you can determine if you're using the right learning rate is by looking at your loss function over training epochs, or as the model is like tuned and trained. If you're taking steps that are too big, meaning your learning rate is too high and you're skipping over your ideal convergence points, you might end up seeing a model that initially seems to be training and then does the opposite. You may also see a model which is learning at a pretty stable rate. That might indicate that your learning rate is too low, that you might want to take bigger steps. Intuitively, if you take bigger steps, you will move faster towards your point of convergence. But there is such a thing as too high a learning rate, where you miss your optimal point of convergence because you are stepping over it. This is all very subjective, and it's definitely one of the black magic arts of building good deep learning models. Stochastic gradient descent is very similar to our standard gradient descent, but rather than performing a parameter update for every training example, it only performs a parameter update for some randomly selected training example or training examples. That is the source of the stochasticity here. So pros and cons. Pros: faster, trains faster than your normal gradient descent methods. Cons: the sampling means that the loss, the calculation of loss is not going to be precise. It's not going to be correct. It is going to be an imprecise estimation of the loss. So you will see much more spiky training results. Minibatch gradient descent performs an update for batches of training examples. So this is kind of midway between standard batch gradient descent and stochastic gradient descent, and is an improvement in many ways on both. Another optimization algorithm is momentum. So the concept behind momentum is that while the other methods are stateless, meaning at every point they don't remember what happened, they don't remember the step they took before, momentum has this extra momentum term here, where the momentum term is intuitively, it takes the past steps, update vector and direction, and a momentum term determines how much you want to weigh it, and then it nudges your next update vector in the direction that your past update went. So basically it's saying that if I've taken 5 steps down the mountain in one direction, and it seems like my 6th step is taking me completely in a totally direction, well, maybe I'm going downhill. I already have momentum, so let's angle ourselves a little bit towards where we went down last time. So Grad is a fairly new optimization algorithm. It's the default for TensorFlow. If you do not designate an optimization algorithm, most of the time you are going to get Grad. It's very nice for dealing with sparse data. The way it works is, instead of choosing one learning rate and applying it across all the parameter updates, it performs larger updates for infrequent parameters and smaller updates for frequently occurring parameters. So this is really interesting in places where you may have millions of parameters, some of which occur quite often, most of which appear pretty sparsely in your dataset. And then we also have ADAM, or Adaptive Moment Estimation Optimization Algorithm. And for this, the key idea here is what is happening is, yes, you are still updating each parameter. That's what all the optimization algorithms are doing. But the learning rate for each one is adaptive. I'm not going to go into too much detail here. What I think is important is that to take a look at this comparison of training optimization algorithm performance across the same dataset, the MNIST handwriting classifier dataset. So this is a test run by Sebastian Reuter. Pretty interesting results. ADAM seems to has the lowest training cost, and it's the most effective algorithm here. Here's a very nice, I think, illustration of how all these algorithms are different. So this is how to read it. This graph on top is the loss landscape of a specific classifier problem where the only change is which optimization algorithm you use. And down here, this is the accuracy of the model. Now keep in mind that we want accuracy to go up over time. We always want high accuracy, and we always want minimal loss. Those two things should go together hand in hand. Now you can see here that SGD, if you all initialize them at the same point, SGD, gradient descent, is slower, but more stable in its directionality. You can also see here that it is the algorithm with the slowest training curve, and that it only catches up to the other algorithms after about 50 epochs. The faster algorithms, take a look at Grad, much more varied in its wiggly in its movement, and even though you can see the accuracy increase over time, this jumps from here to here kind of tell you that if you paused your training at some point there, you would be getting you could be getting weights W at this step and weights W at this step that are pretty distinct from each other, but it converges fast. Now look at the momentum-based methods. So that would be momentum here, and see how momentum moves in a smoother wave and kind of slingshots back around. So the thing with the momentum method is it trains quickly, it moves relatively quickly towards convergence, but because it remembers where it was going last time, it tends to want to keep moving in that direction, and so if you stop training here, you would actually have overshot the convergence point. It takes a while for a momentum-based method to figure out that it's overshot and it has to like turn back almost. And so these are things to think about as you are choosing optimization algorithms and evaluating which optimization algorithms and which learning rates you're picking. Another example, so we have been looking at loss landscapes that have a specific convergence point, but many loss landscapes do not look like that. What if you have something with a saddle point? What if you have something with multiple possible local minima? What might happen is the choice of one algorithm will have you ending up at one local minima, and the choice of another algorithm will have you at another local minima, even if they both initialize at the same point. See here how the algorithms kind of move across the landscape. Different choices of optimization algorithms will move your weights quite drastically. Not all loss functions have a clear convergence point, and it's hard to spot because again, for the most part, we don't build these. We have no visibility into this. This is really just for illustration purposes for people studying. But when you are building deep learning algorithms in n dimensions, you will not have a nice looking loss landscape. You will have to do your best to figure out, extrapolate what's going on here when all you can see is this accuracy graph over time and the loss function over time. So you could have something where your accuracy is close to 100%, but your points and the parameter values are actually sliding off of the function. That is pretty problematic. Another thing to keep in mind is that the initial placement, the initial weights W or initial parameters W, make a huge difference in terms of how fast algorithms train and where they eventually converge. Imagine that you had a initialization here, for example. You might end up then with optimization function that takes you down here or down here rather than here. So another nice illustration of how the different algorithms build you a little bit of intuition about how they train and what they might do in these saddle point scenarios. So here are 4 examples of saddle points. How do you know if your loss function, which is sometimes called an objective function, has a loss landscape with saddle points? Mathematically speaking, there's something you can do. You can take the Hessian matrix of your objective function, and if the eigenvalues are all non-zero and positive, then it has a local minima. If it's non-zero and negative, a local maximum. If the output is a bit mixed, you have to like dig in a little deeper. There's this paper that I linked here that will kind of bring you through the math of that. But again, that's mostly only necessary if you're doing research into this space.